Welcome to a new series of science stuffs with me, Alan Robert. This time we're going to look at the fundamentals of elements, this time starting with the periodic table's history and how it came to be. First, let's take a look at the current periodic table, here provided by sciencenotes.org, who host a freely printable version. As we can see, we have quite an array of elements that have been discovered, and things are arranged in a carefully studied manner with groups and periods. If you can see above the top elements, there is a series of numbers from 1 to 18. Following straight down from these, ignoring the dependent section of the table, these are the groups. Within each group, you can find similar behaviours in the series that follow a trend as you go down to the larger, heavier elements. Reading across a periodic table, one layer or period at a time, we can also observe trends in behaviour. However, we should get to those behaviours and trends in more depth later on in the series. You can also see coloured sections of the table which highlight collections of elements, largely along the division between metallic and non-metallic elements, as well as the different metallic subdivisions. But again, this will be saved for a later date, as this video is largely on how we got here. Jumping back to a long time ago, when people apparently still believed that the first Harry Potter book was true, Henning Brand sought to create a philosopher's stone, with the intention of turning metals into pure gold, in the process making him rich and then inadvertently destroying the economy, rendering gold utterly worthless, and thus cheaper materials inherently more valuable due to their new status as scarce. Brand's lack of economic acumen didn't stop his work, and if a job is worth doing, it's worth doing grossly. So he took urine, boiled it, heated the residues, as you do, and a liquid dropped out and burst into flames. In 1680, this was confirmed to be a newly discovered element, phosphorus. Skimming over things a little, in 1809 at least 47 new elements were discovered, and now with a decent amount of things to look at, patterns could be noted. In 1817, Johann de Bruyne started making collections of 3 elements that he labels as triads, which were, in their triads, very similar in behaviour. Around this time, people started to work out relative atomic masses as well, and taking the average mass across the triad, these values are approximate to the value of the middle member. If we look at the triads themselves, we can in fact see that in these two cases, they show past the groups seen in the modern periodic table. Also, if you look at lithium, sodium and potassium, by taking the average of their masses, you do actually hit 23 mass of sodium. In 1863, John Newland took things a little further and started making a more complete table by grouping things. Put together the 56 discovered elements into 11 groups, ordered them by their masses, and noted his law of octaves in 1864, where there seemed to be a pattern repeating every 8 elements, the first step along the route to the 8 primary groups, ignoring transition metals. This table, however, showed significant flaws, and it proposed that iron should be in the same group as oxygen and sulfur, so a metal with 2 non-metals. Oofed. Moving on to the first proper table that didn't propose that iron was just like oxygen, Dmitry Mendeleev took this idea and moulded it a little in 1869, again using the atomic mass as a starting point, but more factoring in the behaviours and properties in the physical and chemical senses. Due to his rigid adherence to the patterns he proposed, his table featured some blank spaces. This could be seen as a strength or a weakness. Largely a weakness if there were gaps in it, but a strength because he proposed that there were actually other elements that had yet to be discovered that would fit in these gaps. A space, for example, was left under aluminium. Now there's an I before the U and M, so write it out slowly, read it out fast. Biffy Clyro, 2010 I believe. And he proposed that there would be an element that would fit directly underneath aluminium that he labelled Eka aluminium. Later on, this was discovered in 1875 and given the name gallium. His predictions for the properties of what gallium would fit into were actually very, very close to what we observed. This is the most famous example, but this actually happened at least twice more that he found things, predicted them before they existed. If we look at a snapshot of his basic table, you can see things taking shape, but note the lack of helium and the disorganized dumping of iron and copper, for example, into one group, just scattered around there. Now here comes some very famous names from France. Becquerel discovered radioactivity in 1886. However, a New Zealander, Ernest Rutherford, stated that there were 3 key types of radiation: alpha, beta and gamma, which we'll cover at a later date because these are quite interesting. This move into radiation got Marie and Pierre Curie involved. They became legends in the field, and they observed uranium and thorium, which led to the discovery of radium, polonium, and a Nobel Prize for this work. That was a Nobel Prize in physics, bear in mind. They also discovered that Rutherford's beta radiation was a negatively charged particle. I made note, though, that it's the Nobel Prize in physics. Pierre sadly died before Marie got her second Nobel Prize. Her second Nobel Prize was in the area of actually refining plutonium to make it pure, and therefore got a Nobel Prize in chemistry, which then dedicated later work into X-rays. So if we move on into higher society, Sir William Ramsay and Lord Rayleigh, they discovered the noble gases in 1894, tacking them onto the table as Group 0, but on the table presented previously, they're actually listed as Group 18. Interestingly, helium is so named from Helios, for the sun, as it's discovered in the solar emission spectrum and not on Earth. So after we discovered an entire group there, well, in 1897, J.J. Thomson discovered electrons, tiny negatively charged particles in the atom. John Townsend and Robert Milken subsequently evaluated their charge and mass. Later on, that man Becquerel popped back up and proposed that these were actually the beta particles, or at least the same as the beta particles discussed by Rutherford and the Curies. There is some difference in their origin, but they are effectively the same things, and again we'll come back to this later on when we discuss radiation in another episode. Ernest Rutherford, though, has not left our story yet. In 1903, he rationalised that radiation was the decay of an atom. At a later date, this will be discussed in more depth. This is a really, really interesting topic. In 1911, he and Hans Geiger then proposed orbits of electrons around the nucleus of the atom. 2 years later, Niels Bohr proposed that these orbits were discrete energy levels. And the transition between energy levels either led to the emission of radiation, when it went from high to low, that led to emission, or was caused by the absorption of radiation, going from low to high. Rutherford then talked about protons and the nucleus, and this was picked up by Henry Moseley, who refined this into atomic numbers, defined by the number of protons within a nucleus. And he used this to rearrange things in the periodic table and make it a more standard metric rather than using masses. This would be made to look fairly prophetic a few years down the line, and we'll get to that in a second. When Rutherford proposed protons, he looked at the transmutation of nitrogen into oxygen by adding a proton to nitrogen, turning it into oxygen. This was the first time this was ever done. So, as was alluded to, Moseley's idea of replacing atomic mass was vindicated by Chadwick, who identified the existence of neutral neutrons in the nucleus, say that 10 times fast, and noted that the variation of neutron numbers led to isotopes, which were the same element, didn't really change chemical behaviours, but could lead to different physical behaviours and change masses. So therefore, this change should have no real bearing on the periodic table of the elements. Good. This was in 1932, the year that Cockcroft and Walton actually split a lithium atom in a particle accelerator, making 2 helium nuclei. So it's not like splitting the atom has ever caused any issues later on. I mean, it's not like 2 totally destroyed major cities in Japan. The loss and ruination of myriad lives, both in Japan and in every other country where anything has been done on this, and plunging the entire world into a standoff for the latter half of the century. Nothing bad there really at all. For the last point of this journey, in 1945, Glenn Seaborg identified the lanthanides and actinides, best known for their ability to make the periodic table look a bit weird with that pendant group underneath, or by extending it really, really long, not just hanging out underneath, and making it a bit of a mess. They're also used in power stations and weapons of mass destruction. So where do we go now? Well, I hope you've learned a bit about the history, found it moderately interesting, but this is a good foundation as to where we're going to go with it. If we look at where we've been, we can see where we're going to go. So we're going to learn a lot more. In this history, we've unearthed the need to learn about the nuclear structure with protons and neutrons, the existence of electron orbitals, the existence of groups and periods and patterns. And if you've never seen my videos before, then you've learned about my videos, and you can check out some of my other science videos. By the way, if you have enjoyed this video and learned from it, then I've done my job. If you think this has sucked, please tell me why it's bad, where I can improve, what I need to do in the future, rather than just going, lol, that was rubbish. Learning from something that you've done wrong is a good way of reinforcing something you've learned. And I'm always looking to improve, always looking to get better, and always looking to learn. So please let me know if you liked it. That's okay, that's great. I'm not asking for likes. If you disliked it, then please actually do let me know what you didn't like about it. But for now, I hope you've enjoyed this video, and laters y'all!